Project 6, video number 1, the pencil on paper part. We got a wire carrying a current toward us. Wire has a radius capital R, and I'm going to find the magnetic field at a distance little r from the center of the wire first. Well, every time, but first I'm going to do it for a case where little r is smaller than big R. That is for a point inside the wire. Now, it's got a constant current density, so all the current flowing through this part of the wire is flowing through my Amperian loop. And I'm going to go around that Amperian loop. I'll consider integrating around it in a counterclockwise direction. Like that. That'll be my DL. And I think one of the things I want to know is right off the bat is what is the current density? It's uniform across the cross section, but that means that it's just equal to the total current divided by the area of the cross section. So I'm talking about this area, since I'm using all the current, but the current per area is going to be the total current divided by the total area, because they said it was uniform across the entire cross section. So that's I, which is one of the givens in the function, divided by pi capital R squared. Alright, now Ampere's law says the integral of B dot dl is equal to mu 0 times the current through. This is about the Amperian loop, and this is the current through the region enclosed by the loop, through that red surface. And from symmetry, I can argue that the magnetic field extends in loops. So let's put B on there. Centered on the center of the current distribution, and so B is going to be parallel to DL for every step of the way, and therefore parallel to DL makes it so that the dotted product is just the product of the magnitudes. And I'll go, I'll call it A sub R. Well, the current through will be J times A sub little r, where A sub little r is that red area. That's how much current I'm going to get. The current per area times the area enclosed by the Amperian loop, that little dashed line right there. Alright, so by symmetry, the magnetic field has to be the same magnitude at all points that are the same distance. If it weren't, I could tell by spinning the wire a little bit that I had spun the wire by looking at the magnetic field, but you can't tell by looking at the current, and so it has to be the same at all points on my Amperian loop. So this is just going to turn out to be B times the integral of dl, mu 0 J. Now the area of that red region is going to be pi times little r squared. So I'll make that replacement. Alright, then if I integrate all the little length segments making up the loop, I add them all up, I get the total length of the loop. the total length of my Amperian loop, the little dashed line encircling that red region, and so its length is 2 pi times little r. J should be replaced with what it is, I over pi. It's not a given, it's not one of the arguments of the function, so I'll replace it with capital I over pi times big R squared. Capital I over pi times big R squared. That's what J is. And then that's multiplied by pi times little r squared. So what do we have here? I'm going to say this pi cancels this pi. Pi over pi is 1. One of the r's cancels out on this side, and I can say b. I'll divide both sides by 2 pi, so I get b is equal to mu 0 over 2 pi r squared times little r. So the farther out I am from the center, the more current is passing through the Amperian loop, where how far I am out from the center determines the radius of the Amperian loop and the stronger B. So B grows linearly with R out from the center. Alright, now I want to do it again for a case where here's my wire and it's carrying a current I outward. I'll label it with an arrow, and I want to look at points outside the loop. So now my value of little r is bigger than the radius of the wire. And so now when I write integral of b dot dl equals mu 0 times I through the current through the Amperian loop, the current through this red region is all of it. So just capital I. So that'll be mu 0 times I. On this side, once again, the magnetic field extends in loops around the wire, so it's going to be everywhere parallel to dl. Let's get a blue mag field on there. And hence I can say that B is parallel to dl everywhere. So B parallel to dl, so the dot product just becomes the product of the two magnitudes. And then I can also factor it out. All points at the same distance from the center from symmetry. The magnetic field has to have the same value at all those points, and so every term in this infinite sum has the same exact value of B factor, and so I can factor it out. This is 2 pi times the circumference of this Amperian loop, which I'm sorry, B times the circumference of that Amperian loop, which is just 2 pi r. So we got mu 0 over I. And outside we got B is equal to mu 0 over 2 pi I over r. I think I lost the I up here, so let's see if yeah, I just didn't copy it down. So I think I'll put that I over R there. Alright, so this is for R less than or equal to capital R. This should be good for R greater than or equal to capital R. So they should match up. Little r is greater than or equal to capital R. They should match up when little r is equal to big R. Let's make sure that's the case. Oh, I messed up when I popped that I in there, so I want to fix that up. So this is times I times little r. Okay, then when little r is equal to big R, I got mu 0 I over 2 pi times big R over big R squared, so over big R. Mu 0 I over 2 pi times capital R. And when little r here is equal to big R, I get mu 0 I over 2 pi capital R. So they match up at little r is equal to big R. In other words, the magnetic field at on the surface of the wire is the same whether I use the formula that was good for inside the wire or the one that's good for outside the wire. So inside it grows linearly with distance from the center of the wire, and outside it dies off like 1 over R. Alright, so let's write a little function that does that. Function I think I'll use the symbol B to represent the magnetic field, and mag field as my function name. And we had a very specific argument list to capital I, capital R, little r. Capital I, capital R, little r. Just want to make sure I got those. I first, then capital R. Yeah, I, capital R, little r. Alright, those are the arguments of it. And then, let's say mu 0 equals, it's from the formula sheet, it's 4 pi times 10 to the minus 7th. I think I'll write it as pi times 4 times 10 to the minus 7th. And the units are Tesla meters per ampere. I'll put them in here, but not into the actual code. And what else do I need? This is one of my formulas. I think I got everything, so I'll just say if R is less than big R, B is my return variable, B equals the first formula, which I think was mu 0 over 2 pi I over capital R squared times little r. And make sure I have that right. Mu 0 over 2 pi capital R squared, then times IR. Mu 0 over 2 pi capital R squared times IR. Okay. Else b equals mu 0, it's this one right here, over 2 pi I over little r. And that'll end that if statement, and then I end the function. And I think I've actually written the whole function there. Remember, when you're doing this outline, you can just write in English how you're going to do it. Can't quite type it in like that because I can't type in mu sub 0, but I think I actually have the whole function there. So that should do it for project 6, video number 1, the pencil and paper part.